Nodal analysis is one of the most systematic methods for solving circuits. The key idea: write Kirchhoff's current law at each node. Express each branch current in terms of node voltages using Ohm's law. Here is the four-step method. Step 1. Choose a reference node, also called ground. This will be our 0-volt reference. Step 2. Identify all other nodes in the circuit. Step 3. Write KCL for each node. For every branch, write current as voltage difference divided by resistance. Then set the sum equal to 0. Step 4. Determine the sign of each current source using the entering-leaving rule. If a current source enters a node, write it as minus in the equation because it leaves as branch current. If it leaves the node, write it as plus. Once you follow these four steps, you get a system of equations in node voltages. Let's apply the method to a concrete example. Here is our circuit. We have 3 resistors, 8 ohms between node 1 and ground, 16 ohms between node 1 and node 2, and 12 ohms between node 2 and ground. We also have 2 current sources, a 9 ampere source entering node 1 and a 3 ampere source entering node 2. Our goal is to find the voltages at node 1 and node 2. Notice we already chose the bottom node as our reference ground. So we need 2 equations for 2 unknowns, V1 and V2. Now let's write KCL at node 1. First branch, the 16 ohm resistor connecting node 1 to node 2. Current flowing from node 1 to node 2 is V1 minus V2 divided by 16. Second branch, the 8 ohm resistor connecting node 1 to ground. Current is simply V1 divided by 8. Now the current source. The 9 ampere source is entering node 1. By our rule, entering means minus 9 in the equation. Putting it all together, V1 minus V2 divided by 16 plus V1 divided by 8 minus 9 equals 0. Let's multiply through by 16 to clear the denominator. We get V1 minus V2 plus 2V1 minus 144 equals 0. Simplifying, 3V1 minus V2 equals 144. That is our first equation. Now let's write KCL at node 2. First branch, again the 16 ohm resistor. Current flowing from node 2 to node 1 is V2 minus V1 divided by 16. Second branch, the 12 ohm resistor to ground. Current is V2 divided by 12. Now the current source. The 3 ampere source is entering node 2. Again, entering means minus 3. Writing the equation, V2 minus V1 divided by 16 plus V2 divided by 12 minus 3 equals 0. Multiply through by 48 to clear denominators. We get 3V2 minus 3V1 plus 4V2 minus 144 equals 0. Simplifying, minus 3V1 plus 7V2 equals 144. That is our second equation. Now we solve the 2 equations together. Equation 1. 3V1 minus V2 equals 144. Equation 2. Minus 3V1 plus 7V2 equals 144. Adding equation 1 and equation 2, the 3V1 terms cancel. We get 6V2 equals 288. Therefore, V2 equals 48 volts. Now substitute back into equation 1. 3V1 minus 48 equals 144. 3V1 equals 192. Therefore, V1 equals 64 volts. Let's verify. At node 1, the current leaving through the 16 ohm resistor is 64 minus 48 over 16, which is 1 ampere. Through the 8 ohm resistor, 64 over 8, which is 8 amperes. Total leaving 1 plus 8, which equals 9 amperes, matching the current source entering. At node 2, 48 minus 64 over 16, which is minus 1 ampere, meaning 1 ampere entering from the 16 ohm branch, plus 48 over 12, which is 4 amperes. Total entering, 1 plus 4 equals 5, and we subtract the 3 ampere source entering, giving 0. Both equations check out. Let's summarize the nodal analysis method. First, choose a reference node. Second, identify all other nodes. Third, write KCL at each node, expressing branch currents as voltage differences over resistance, then set the sum to 0. Fourth, apply the entering-leaving rule for current sources. If the source enters the node, write it as minus in the equation. Once you have the equations, solve the linear system to find the node voltages. In the next video, we'll extend this method to supernodes, which handle cases where a voltage source connects two non-reference nodes directly.